everyone, and let me specify that very quickly. Planned migration. We're still working on it. But yeah, my name is Thomas. I work at Salesforce. More specifically, I work on the Einstein platform. That is it's an AI layer of Salesforce. And more specifically, my team owns the Einstein data lake that feeds data, that provides data to ML systems throughout Salesforce for modeling or scoring purposes. And so today I'm going to tell you why we are building a new abstraction in a data lake called tables, and why we thought that what we have currently, datasets, is not enough. And I hope that the rationale I'm going to lay out for you might be useful in your own companies for your own lakes. So let me start by the end. The key takeaways are as follows. Immutable datasets create coupling between data consumers and data producers, especially for Firehouse kind of data producers, meaning you have an object that you care about in your lake, and new records or updated records come in for that object on a regular basis. And so that coupling makes life harder for consumers because they need to be aware of how the producers puts data in the lake. Instead, we think that adding a new abstraction called table, think of it right now as a virtual spreadsheet, if you will, append-only spreadsheet, essentially hides the hydration from the consumer. The consumer simply knows that there is a table. An object is not anymore an ever-growing set of datasets. It's just this ever-growing table. And we think that not only will that make life simpler for the consumer just on the face of it, because it doesn't have to deal with a set of datasets, but this table abstraction will also enable us, meaning the team owning data lake, to provide some things that we cannot do today on behalf of the consumer. That is schema evolution. Hey, what if my object now, one of its fields was renamed? Versioning or time travel, being able to see the data as it was in a point in time, and better predicate pushdown so that we minimize what's being sent to the compute layer used by those ML systems. Today, unfortunately, it's up to the consumer to deal with that, and this is usually tedious or tricky. So in essence, what I'm saying is datasets are very nice for data producers. You can just keep adding datasets to your lakes, that's great, but it makes life hard on all the consumers of your lake. Instead, with tables, it's a bit reversed. It's a bit tougher on the producer, but it's much, much easier for all the consumers of your lake. And since we have many more consumers in Salesforce of our lake than we have producers, we think it's a good trade-off to make. We make it simple for the many. So those are the key takeaways. Keep them in mind as we go through our journey. So let's start by some context. So as I said, I work on the Einstein platform, which is an AI layer at Salesforce. And so if you ask a data scientist on Einstein platform, hey, what is the main lesson learned? He will tell you, or he or she will tell you, three things. Customer-specific models beat global models. That means that as Salesforce, if you have a feature that tries to predict, say, churn on accounts, it's probably better, and I will explain why later, to create models per customer, they'll be more accurate, than a global model that applies to all customers. Learning is number two. There are many, many use cases at Salesforce that can leverage ML or AI, and way too few data scientists. 2 points together mean we need to automate the creation and the operation of a lot of ML pipelines at Salesforce. Essentially, at least one per feature per customer. And well, that's why we're here. The silver lining, though, which is the third learning, is that the majority of business data that we deal with is structured. And this is a boon for the data scientists because they can leverage the structure to automate machine learning as much as possible. If you're interested, this is not the purpose of this talk, but if you're interested, check out our open source AutoML library called Transmogriff AI. It's pretty cool. I'll link a slide at the end. Now let me double click a little bit why customer specific models beat global model and what is the difficulty there. For those who are familiar with Salesforce, account is one of the most standard objects. It's what sales rep around the world on a daily, on an hourly basis interact with through the Salesforce UI to track who they're selling the product to. And so it has attributes like name, address, and a lot more that I cannot display here. The power of Salesforce, however, is in its customization capabilities. If you work for Acme Corp, you might see, as a sales rep, you might see a custom field or a set of custom fields in there that are specific to Acme and that have been added to the schema of that account by a Salesforce admin at Acme. In this case, for example, churn risk. That would be different if you work at Wayne Enterprise and have their own set of custom fields. And if you work for Wayland, you might have even custom objects that have been created by the admin. And so that means that in our lake, we have to deal with a lot more that you might have thought, a lot more schemas that you might have thought, tens of thousands, because customers customize the objects they work with. So that's obviously creates some difficulty for us, but it's very important that we do capture those custom fields. Those custom fields have been purposefully created by the customer, and therefore they are very likely to contain information that is predictive in nature. And so we would like to ML systems at Salesforce want to leverage that information. So it's very important for us to grab that. And unfortunately, with that comes a whole slew of difficulties like handling schema changes and so forth. So, as I said, my team owns a data lake that provides data to those ML systems. So a data lake is usually a simple, compliant, scalable data API. Something specific to Salesforce is that we had to work very hard to ensure tenant isolation, meaning like an ML system building a model for when enterprise should not by accident use data from Acme. That's very important at Salesforce, and so we had to do a lot of work to make that a reality. And our data lake is optimized for ML access patterns, meaning get all the data for modeling or get the latest data for micro-batch predictions. It's not a general purpose lake, it's an ML lake. And one of the other things that we had to work a lot on is automate the hydration of that lake, meaning like for every model, customer model that is being built at Salesforce, we need to essentially automate the constant hydration of the lake for that object, meaning, for example, account at Acme. And so when we started, we decided to go with the simplest thing, which was immutable datasets. Well, we're going to see an example in a few seconds. It was the simplest to get started, and it was also the one we felt would scale well at the beginning. And so what is a dataset? It's essentially metadata about some piece of data. That metadata lives in a metadata database and contains pointers or locations where the actual data lives in a blob store. Pretty straightforward. Let's take an example. This is an example of a dataset. Let's start by the bottom. Datasets usually contains attributes that are used by the system that's going to consume the data, say the Spark or TensorFlow or whatnot, that needs to get the data to build a model, say. And so those fields are usually schema and a manifest list that contains a location of the actual data, and maybe some stats that the framework you use can make good use of. Dataset will also usually contain metadata related to the lifecycle maybe a status, some lineage. This is what you would use to do GDPR kind of processes and compliance in general. And then it contains attributes that will help consumer system discover the set of data sets that they need for the task at hand. Some obvious one is, hey, what is the object that you're looking for? And so that for us is a combination of, in this example, account, and tenant, meaning customer, in this case, Acme. And then what I could generally describe as tags. For example, the type, is it a snapshot or an incremental data set? And a few other things that will help the consumer system query the data lake and find the right data set for the task. Now, you might already be able to tell that unfortunately, those tags essentially leak hydration details to the consumer, and the consumer of the data lake needs to understand what those tags are. They're a contract between the producer and the consumer, and they need to be aware of this in order to properly request data. And what's interesting is the consumer system knows what it wants in terms of the data. We're going to see a few examples. But this abstraction allows the consumer to translate this data request into a metadata request through those tags or through those attributes. Could be first-class attributes, doesn't really matter, but they need to translate that in terms of metadata. So they need to be aware of what those are. That's a little bit unfortunate because consumer systems really don't care. They just want a schema and some file locations. And we're forcing them, so this is abstraction, to be aware of that abstraction. So that's already, I would say, one limitation of data sets. Makes life already more complicated for the consumers. They need to be aware of that. Another set of issues is that through that abstraction, me as the owner of my team as the owner of the data lake cannot provide more cool things to the consumer. For example, the handling of schema drift. As we mentioned earlier, it's very important for us to capture all those custom fields that change over time. And today we cannot do a great job at it. Let me explain why. Here is a timeline of data sets that was created just for the sake of this example. And so at time 3 here, a snapshot was created with 1,001 records. The schema at that time was A, B, C. Okay, very straightforward. At time 4, a smaller data set was created with just 4 new records for, say, account at Acme. But something major happened at that time. An admin changed the field type, renamed the field B into Z. And at time 5, the admin changed again the schema and removed field A, say. Also with a very small number of new records for that object. As a consumer system, you just want to ask, hey, get me all the data for that account, for Acme, and that way I can build a model. That's ideally what you want. Unfortunately, assuming you work your way through the metadata, you will probably get to dataset 3, 4, and 5, but you will not have the knowledge that field Z is simply a rename of field B. You either need to, as a consumer of the data lake, figure that out by yourself, error prone, or you need to accept that you might not be loading the values that were in field B for dataset 3, which is unfortunate, again, because so much of our accuracy in our automated machine learning depends on getting those custom fields. What you would like ideally is simply not have to care about that and just have the data being aligned for you. Another limitation, reproducible discovery. You can ask, say at time 4, you ask the data lake, hey, get me everything that's new since time 3. Again, you can probably work your way through that using those metadata. You will get dataset 4, that's nice. You do the exact same request at time 5, you will get 2 datasets. You have no way today to say, hey, I want everything that's new since T3 as of time 4. And that is a problem for ML systems because they, for troubleshooting and for consistency, they usually want to be able to feed again the exact same data into one of those processes to help with troubleshooting or help with consistency. And so today, we don't provide that as part of the data lake, and the customer has to deal with that, mostly by tracking dataset IDs. And finally, the third thing that we cannot yet do with that abstraction on behalf of the customer is better predicate pushdown. I actually understated something at the beginning. I said, customer models beat global models. That's an understatement in the sense that segmented customer models now beat customer models. Meaning like if Salesforce wants to predict churn at Acme, it should not necessarily create one model, but maybe a set of models, one per geographical region, for example. And so ML systems want to now have access to just a segment of the data. For example, get me everything since T2, where geo equals US. Now this is interesting because if in that tag system or whatever attributes, geo is not surfaced, tough luck. You cannot request just that segment through the current API, and you will have to get, again, 3, 4, 5, all the data, and deal with that on your end as a consumer system. That's unfortunate. What you would like is just to be able to say, hey, I just want the US geo, and you get a subset of the data directly. So those three things we cannot easily do on behalf of the consumer of our data lake, and they have to do it themselves. This is, so those three reasons, plus the fact that the consumer cannot express its data request directly, has to go through a metadata layer, pushed us to investigate a new abstraction, tables. So what is a table exactly? As I said earlier, instead of thinking for an object to be a collection of a set of data sets, an ever-growing set of data sets, think of it as an ever-growing table. In our case, a table, an object is defined by an entity, say account, for a given customer, say Acme, and you have a table ID. Now, as a consumer system, you can request data by posting what's called a scan for that table ID. The canonical scan is an empty scan, which is essentially asking, hey, what do you have in your table? In this case, the scan response will be, okay, schema and manifest mostly, that's what you care about as a consumer system of the lake. And so you will see field Z and C, and you will see a bunch of paths that properly align with regard to schema drift. If you want the latest data, you just add a pushdown filter. For example, timestamp greater than 3, you will see almost the same scan response, except the manifest will be much smaller. And so your system will consume less data, just the data it needs. Ideally, that API should also support time travel. So through a parameter, for example, as of time 4, you should see two differences here. You still see field A, because it was not deleted at time 4. So it's A, Z, and C. And you don't see the latest blobs of data, because they were not there as of time 4. Finally, get a segment of the data. Well, it's exactly the same as for latest data. You add a pushdown filter, geo equals US. Doesn't really matter what your field is. The data lake should attempt to prune the manifest as much as possible and return something that's as close as possible to your filter. So this is ideally what we would like this abstraction to be. Now, as I said earlier, we're still in the process of building this, and we are currently trying out the implementation of that using Iceberg, which is a project that came out of Netflix, now an Apache project. And Iceberg is a table format that makes a couple of important things for us easy or simple. First, it supports schema evolution with no side effects. So it's simple to add, drop, update, or rename columns correctly. Through the format, it's also easy to do time travel, which again we said was important for ML systems. And Iceberg allows for partition layout evolution, which means based on the data volume and the query pattern, we can adjust the partitioning so that predicate pushdowns are more effective when a request is made to the lake. So again, this was just painting the rationale for us to work on this abstraction. And again, the main idea is datasets were great for producers. You just push datasets, push datasets, push datasets, very, very straightforward. Unfortunately, you make your life a lot harder for your consumers because they need to be aware of your metadata scheme, essentially, and they need to be able to translate a data request into a metadata request. And then they had to do all the difficult stuff around schema handling, predicate pushdown, and reproducible queries on their own. With tables, we're going to make it harder on the producer of data, but consumers will reap great benefits. And because there are many ML systems at Salesforce that want to consume data, we think it's the right thing to do. Thank you very much for your attention. I'm going to take some questions. Just before that, I'm just showing you a slide about transformergraph.ai. If you're interested in how we automate machine learning, take a look. It's pretty impressive. And if you have structured data, it creates pretty good model, interpretable model, which is important in those days for you to use. So thank you very much.
I'm told it helps if you repeat the question up there on that mic too.
Thank you. So I have a question regarding any messaging platform that is used by Einstein.
Sorry, I'm not sure. I cannot hear you super well.
So the question is, does Einstein integrate with any messaging platform? Let's say
a message platform? Can you give me an example? Sorry.
So an example would be like a distributed publish subscribe system.
Yes, sorry.
So
yes.
why I'm asking this, the idea behind this question is that if you integrate with systems like this, they already allow you to take care of schema validation and schema evolution. That does exactly what you were showing in the first place.
Yes.
So, that's the question.
It's a very good question. My answer so the question was, do we integrate with a messaging platform or a pub system because that could take care of schema drift for you? The answer is twofold. I think Salesforce is a collection of systems now, so you might not have that for every data source. So that's one answer. The second answer is, the second part of the answer is, those are still fairly new at Salesforce, even those who have changed data capture. This is still a little bit new, and so we have been relying a lot on pooling and slowly moving towards stream. But I would also add, though, that tables are a much better abstraction when you're ready to get stream data into your data lake, because the data set doesn't make a lot of sense. It makes a lot of sense when you do pooling. It does a lot less sense when you do stream hydration of your lake. So even in that case, I would still argue that table is a better abstraction.
Hi. Oh, sorry, a bit loud.
Hello.
I guess my mental model for what you're talking about is essentially a table is like an apparently mutable virtualization of underlying immutable data sets that are sort of nominally supposed to be continuous, but they can have different schemas and metadata through time, right? Does that make sense?
Yes. Yeah, it's correct.
Fantastic, thank you.
And that's exactly right. You hide what's underneath so that the consumer doesn't have to deal with that. I deal with that on their behalf.
All right. Thank you very much.
Thank you very much.